All right, we have to finish talking a little bit about what we've talked about when we talk about oxidation solutions, and then a little bit review of what we've talked about for solutions from last year. And this is the end of chapter 4. So when we talk about oxidation numbers and oxidation solutions, we're going to talk about what we call ox-redox reactions, or what happens when we have an oxidation and a reduction occur in the same reaction. And what happens is one particular atom in a single replacement, or what they call displacement, a single displacement reaction. Really, something is oxidized and something is reduced. And when that happens, you're going to get a type of reaction. So in displacement, or what last year we termed as replacement reactions, either single or double, you're having something get oxidized and you're having something get reduced. So if we look at a quick example here, we have copper, and I'm focusing really on this equation at the bottom. You have solid copper, and you mix in an aqueous silver solution. And what happens is the silver attaches itself to the piece of copper, and you get a reaction where silver becomes a solid and copper becomes the aqueous solution. And what you can see here is copper starts off with a charge of 0, ends up with a charge of +2. Silver started with a charge of +1 and ends with a neutral charge. So you can see that in this case, silver is reduced because it's losing electrons, and copper is oxidized because it's gaining electrons. All right. However, if we try the reverse reaction does not happen. And that's because silver, the following requirements aren't met to have an oxidation ox-redox reaction, and they are not going to mix. And why does that happen? Well, when we talk about displacement reactions, particularly single displacement reactions, remember we have to talk about the activity series. Now, you won't have to memorize the activity series, but remember, the activity series gives us a level of which elements are the most active. So lithium will replace everything on the periodic table. Lithium will replace everything, where gold is hardly going to replace anything. And in a single replacement reaction, the element has to be above, on the top of the chart, above the other element it's replacing to have that reaction go forward. So if we look here, we have copper and silver. They're right next to one another. So copper will replace silver, but silver will not replace copper, and that is due to the activity series and all the requirements of the activity series. So that sums up kind of oxidation numbers. We will continue to talk about oxidation numbers. We'll have a chapter devoted to ox-redox reactions later in the year, but kind of wanted to introduce oxidation numbers to you. Last thing we need to talk about when we talk about solutions is how do we measure concentrations of solutions and how do we make solutions. Well, how do we measure concentrations of solutions? You guys already know how to do that. Molarity is capitalized with a capital, or abbreviated with a capital M, and it's equal to moles divided by essentially liters of solution. Now remember, though, there's molarity and there's molality. We are not going to deal a whole lot with molality. We are going to deal mostly with molarity. There are a handful of instances which we'll do with molality, but when we talk about solutions and making solutions, we're going to use molarity. So, if I ask you to make a solution, how are you going to make a solution? Now, you are not obviously going to have to make a solution on the AP test. This is just good common lab practice if you're going to take college classes in chemistry. So, you're going to find the molarity of the solution. The molarity of the solution is going to be moles divided by liters. Well, you know exactly, how much weight of a substance you're going to need. You know exactly how many liters of water or solvent you're going to need. So those are the first things. You're going to weigh out how much you need, and you're going to get the amount of liquid or solvent that you need. Then, really, if you're going to look at this, it says draw half and half into the pipette. Really, what you're going to do is you have your total amount of grams of your solute that's going to be dissolved. You have your total number of liters of solvent. You're going to add half your solvent. You're going to put half your solvent in a new beaker. Then you're going to add all of your solute. You're going to mix it around. Once you've mixed around your solute, then you're going to add the other half of your solvent or water. So again, real quick, the easy way, you don't have to worry about writing down dilution here. The real easy way to make a solution is I'm going to get solvent, my water, and my solute, whatever I'm dissolving. I'm going to fill the beaker half full with my water or my solvent. I'm going to put in all my solute, mix it around, stir it up. Once it's mixed around and stirred up, I'm going to add my other half of water or solvent. Now, let's say I have a solution which is 0.20 molarity, and I want a solution of 0.14 molarity. How do I dilute something? Well, we're going to use this equation. MC times VC is equal to MD times VD. And in this case, you could use M1 and V1 and M2 and V2, but MC and MD stand for molarity. We're talking about molarity of our initial substance in C and our final in D. And V stands for how much volume we're going to use of each one. So you may get a question like I used on the last slide. We're going 0.21 molarity or 0.20 to 0.14 molarity. How many volumes or how many milliliters am I going to need? Well, I'm going to start with my capital M here is 0.20. My second molarity is 0.14. Now, your VD is going to be how many liters of that solution you want. And this is going to be how much you want to make. So that's going to depend on the lab. But let's say I want half a milliliter or half a liter. Now I'm going to do the work, and to dilute this, I'm going to figure out exactly the volume of that solution that I need to use. And that will be my answer. We will do a couple of these practice problems in class. If you are still confused on this, we will do a couple problems in class on dilutions. So that is kind of how you're going to dilute a solution. You can use molarities in stoichiometric calculations. Well, how do we do that? Remember, you can go from grams of A to moles of A. Anytime you're in moles, you can figure out liters or volume. Because remember, molarity is equal to moles divided by liters. So once you have moles, you're going to know how many liters of a substance you have. You can convert using your molarity. And that is what you do when we use titration. And you reviewed how to do titration yesterday in the lab. It's a simple process where you just are going from, really again, grams of A to moles of A to moles of B to grams of B, and then you are using liters to find your solutions and concentrations. It's kind of that four-step process of titration. We will work on some titration problems, but we've really focused on our titration aspect in the lab and reading a titration curve in the lab. We will work on some dilution problems as well tomorrow in class, but that concludes section 4.3.